Introducing the ARC Particle Analyzer by Spectradyne. Meet Nak Do, our senior application scientist here at Spectradyne. She will be using our ARC Particle Analyzer to quantify a subpopulation of fluorescent extracellular vesicles in a complex mixture. Specifically, we'll measure the concentration and size distribution of GFP-expressing vesicles in a much higher background of non-fluorescent vesicles. Why did we pick this measurement as an example? Because no other technology can successfully execute it. These particles are sub-100 nanometers diameter, weakly fluorescent, and don't scatter light strongly, so accurate concentration measurements by flow cytometry or fluorescence NTA are not possible. These particles also have heterogeneous optical properties, so a single refractive index for all particles cannot be assumed to determine their size by flow cytometry. And techniques that require immobilization of the particles on a surface take a long time and aren't quantitative for absolute concentration. Only the ARC is capable of accurately performing this measurement because it uses MRPS to directly measure the size and concentration down to 50 nanometers, while simultaneously measuring single particle fluorescence to identify the subpopulation of interest. Let's get started. First, load just 3 microliters of the sample to be analyzed into our microfluidic cartridge. Then simply open the cartridge interface on the instrument, put the cartridge in, and close the lid. The indicator lights clearly show that the instrument is now ready to go. And from this point on, sample analysis with the ARC is controlled entirely by our software. In the software, enter a few details about the cartridge and a short sample description. Then we can start getting the instrument and cartridge ready for measurement. A key feature of the ARC is that the focus and alignment of the excitation beam and collection optics is completely automated, without separately having to run a dedicated sample. Simply press autofocus and align, and wait for the process to complete. Each time this process is run, the shape and location of the excitation beam are measured, and the results are stored with the metadata for subsequent runs. This feature means a much simpler workflow than for flow cytometry and ensures repeatable results from run to run. This image is showing us that the excitation beam is perfectly aligned directly over the MRPS sensing constriction in the microfluidic cartridge. Once the optics have been aligned, it's a single click to begin acquiring data. The microfluidic analysis cartridge is automatically primed with sample and running buffer, and the correct fluid flow patterns are established for measurement. Particles are analyzed in 10-second acquisitions, and the raw data is displayed after each is complete. Let's zoom in for a closer look. Particles are detected electrically using Microfluidic Resistive Pulse Sensing, or MRPS. The MRPS measurement is shown in blue, and this downward spike is an example of a particle detection event. You can learn more about how MRPS works on our website. Now with the ARC, we're not only counting and sizing particles, we're also simultaneously measuring each individual particle's fluorescence. This particle in particular generates a large amplitude signal in the FITC detection channel and a smaller amplitude signal in the PE channel. Each acquisition is processed in real time by our auto analysis engine. The auto analysis engine also offers a variety of ways to view your data in real time. The live CSD shows the particle size distribution as measured by MRPS. So this is showing us the distribution of concentration versus size for all the particles detected so far. The live CSD also shows us the particle size distribution for the subset of particles that exceed a brightness threshold in each fluorescent channel. We can immediately see from this that there is a well-defined subpopulation of particles in the sample that are fluorescent in the FITC channel. These are the particles we're looking for. How can we be sure these are real particle events? The ARC uses MRPS, a non-optical technique, to count and size particles one by one without making any assumptions about particles' optical properties. This means we know for sure that every fluorescent particle is a real particle, and not an artifact of using an optical technique to detect particles smaller than the wavelength of light. The auto-analysis engine permits a variety of parametric scatter plots to be viewed in real time, or as a function of time. This particular view shows fluorescence amplitude in the FITC channel versus true particle diameter. Remember, no assumptions have been made about the particle's physical properties in order to calculate their diameters. And this is what we're after. You can see in this plot that the majority of particles in the sample are non-fluorescent. The fluorescence amplitude of these events are below the limit of detection. However, the particles of this population are clearly fluorescent. These are precisely the GFP-labeled EVs we're looking for, and we can see them being detected in real time. After counting sufficient particles to ensure statistical confidence in the concentration measurements, in this case, a few thousand particles, we can end our run. Now we can combine the data into a single record for more detailed analysis in our data viewer software. Our viewer software enables powerful, in-depth analysis of all the data collected on the ARC. Our software has many powerful capabilities, but for now, we will give a brief overview of key features using the data we've just collected. First, load up the data from the run we just completed. The primary strength of the ARC is its ability to measure accurate particle concentration and size of specific particle phenotypes in a complex sample, which is precisely what's shown here. This plot is giving us the particle concentration as a function of size for 3 different subsets of the sample. All particles, and remember, these are real particles detected by MRPS, FITC-positive particles, and PE-positive particles. This plot immediately shows us what we came here to find out, which is the concentration as a function of size of the GFP-expressing EVs in this sample. We can make quantitative measurements over any size range in this sample. On this size range, the GFP-positive EVs are present at a concentration of about 5 × 10⁸ particles per milliliter and represent a little over 3% of all particles. We can isolate the fluorescent particles in the sample using a custom or predefined gate. For this sample, we can define a new polygonal gate to include only the particles having a diameter of FL1 signal within our range of interest. So, just how bright are these particles? We can answer that question with this plot, which shows the concentration of particles in the gated population as a function of brightness in the FL1 channel, which is configured for detecting FITC. Note the units of brightness here are absolute. Spectradyne makes every effort to report its data in absolute and traceable units whenever possible, in contrast to flow cytometry, where results are typically presented in arbitrary units that can't be compared between labs. On the ARC, fluorescence measurements can be presented by default in absolute transferable units of MESF. Now, we select the range and fit the peak in the distribution to a Gaussian curve, which reasonably approximates the distribution. We immediately find that the average brightness of this subpopulation is a little over 200 FITC-MESF, and we can directly read the concentration from the fit over the selected range. Today, we've shown you the simplicity and power of Spectradyne's ARC particle analyzer. The ARC delivers accurate measurements of particle size, concentration, and simultaneous single-particle fluorescence at the nanoscale, all in an easy-to-use desktop system. Reach out to our sales team to learn more.